All right, so let's go over this. All right, for our first one, okay, actually, let's copy it over here. Okay, so our first one, 1 mark for their givens, okay? They told you it's copper, so the specific heat capacity of copper is 0.390 joules per gram degree Celsius. Okay, it also tell you the amount of energy required, 8,000 joules. Okay, and the temperature change, okay, is 35 minus 20, which is 15 degrees Celsius. So give them a mark if they've got that. All right, obviously it's an E equals MC delta T question. Because you knew this was a specific heat capacity quiz, you are not getting a mark for that formula. On an exam, you would get a mark for that formula for recognizing the type of question. Okay, now we need to manipulate here to find mass. So if we want to get M by itself, we divide the other two things over to the other side. Okay, so E over C delta T gives us M. Give them a mark if they showed that manipulation. They can also have a mark for plugging in the numbers correctly. 8,000 joules, okay, divided by 0.390 times 15 degrees Celsius. Okay, so a mark for that. And the mass comes out to 1,367.5 grams. Fourth and final mark. Okay, questions on that one? All right, for number 2, again, they'll get a mark for their givens. We were told the mass of iron here was 300 grams. We're told it's iron, so it's 0.460 joules per gram degree Celsius. And we're told the initial temperature, 4 degrees Celsius, and the amount of energy input is 1,900 joules. Okay, give them a mark for that. Again, this is the formula that we're going to use, E equals MC delta T. You're not getting a mark for that today. Okay, manipulating for delta T means to divide both sides by MC. All right, so give them a mark if they have E over MC equals delta T. All right, plugging in the numbers, that means 1,900 joules, okay, divided by 300 grams times 0.460 joules per gram degree Celsius. Okay, so that equals delta T. Okay, so give them a mark for plugging in the numbers correctly. When we do that, delta T comes out to 13.8 degrees Celsius, but that's not where this question ends. This is as hard as a specific heat capacity question gets. If I want to find the final temperature, I need to take the initial temperature and add the change in temperature. So if they showed somewhere 4 plus 13.8 degrees Celsius, they can have a mark, and their last mark will be for the final temperature, 17.8 degrees C. All right, so that one's out of 5. Okay, give them a mark out of 9. Sorry, question? Yeah, you can just show me the formula. Just show me E equals MC, or sorry, E over MC equals delta T. You don't have to show me the crossing off. Yeah. Okay, give them a mark out of 9, guys. Let them see it. Put it in the box, please, and then quickly back to your desks. Few things I want to go over here in terms of the stuff we covered in Lesson 2. Okay, in Lesson 2 we talked about solar energy budgets, and we talked about heat transfer, okay, and things like that. All right. The 3 things that can happen to light when it strikes the earth, what were they? Okay, it could be reflected. All right, what else could happen to it? Okay, used, okay, slash converted, and what process did that? Right, through photosynthesis. Okay, okay, important to remember these things. And the last thing that could happen, it could be absorbed. All right. So the stuff that gets reflected, we don't worry about. It's gone. Okay, it might come back a second time if it reflects off, the greenhouse gases and whatever, and comes back down, right? Used, converted for photosynthesis, certainly that's important because that's the source of chemical energy, okay, that runs essentially all the ecosystems and organisms on Earth. When the energy is absorbed, okay, it could be absorbed by the atmosphere. It could be absorbed by oceans, lakes, rivers, the hydrosphere. Okay, it could be absorbed by the lithosphere, the solid part of the Earth. All right. Now, there's a few things we need to remember about those things. First off, what do we call it? What do we call the amount of energy that gets absorbed? There's something that affects the amount of energy that gets absorbed. Starts with A. Nope. It has to do with parts of the Earth reflect and absorb more than other parts. If it's covered in snow, it has a really high this, and if it's covered in trees and rocks and dirt, it's got a really high something else. Short word, starts with A. That's, well, it starts with A, but it's not really short. Albedo. Okay? Something you're definitely going to need to know. So I guess we all got to look that one up again, okay, at some point. Now, albedo has to do with the amount of radiation or radiant energy that can be absorbed, okay? And we said that energy could be transferred by three methods: conduction, convection, and radiation. These are crucial concepts for this unit because I will ask you on your unit exam to apply them to a practical situation. Could be, I would ask you to maybe design a building that could do a certain job, maybe keep things hot or keep things cold, okay, things like that, and you would have to incorporate these methods of heat transfer into that idea. All right? Now, we've already said that albedo can affect the amount of radiant energy that is absorbed. All right? So if I want to absorb a lot of energy, what colors do I want to use? Black, dark, right? Okay? So black colors absorb more, okay? Okay? White colors or light colors reflect. All right? Everyone with me there? Right, so these are important things to know because if I want to keep something cool, I probably want to make it light in color because that will help to reflect away a lot of the incoming energy. Right? Same idea, if I want to absorb something, I want to make it dark in color so it absorbs lots of things. Okay, everyone follow me there? We talked about also the tin foil has two sides, right? The reflective side and the dull side. Okay, and that we wrap a potato appropriately. We put the shiny side in so that heat is absorbed by the dull side, and then it reflects back and forth through the potato multiple times by reflecting off the shiny side. All right, so that's how we deal with radiation. We either reflect it or we absorb it. Okay, now once it's absorbed, it can be transferred by one of these two methods, okay? Either by conduction or convection. Now, conduction occurs in what state of matter? Solid, liquid, or gas? No. Okay. Conduction happens when energy can be physically transferred between particles by them running into each other. Solids. Okay? Only solids have their particles close enough together to actually run into each other often. Okay? In liquids, they're too far apart. Conduction basically doesn't happen in liquids, and it almost never happens in gases. Okay? So conduction happens in solids. All right? And it is slow. Okay? And there has to be contact for it to occur. So for example, if I'm going to transfer energy from, let's say, like a hot piece of metal to something else, I would actually have to touch them together for that to occur by conduction. Okay, everyone follow me there? Yes? Yep. All right, so conduction can only occur when things are in contact with each other. If I want to prevent conduction from happening, What do I want to create? Well, not a barrier, because if there's a barrier, there's contact, right? I want to create separation. Okay? If they're not in contact with each other, I can't transmit energy by conduction. Agreed? Okay? This is why insulative materials usually have either a vacuum or lots of spaces inside that are filled with gas, okay, or air or something like that that does not conduct. Everybody follow me? Okay, if you look at like a thermos, okay, or any like insulated mug or anything like that, okay, typically what you have is two cylinders, right? You have an outside cylinder and then you have an inside cylinder that actually holds the liquid, right? So it looks, okay, so you have your outside kind of container, okay, and then inside of that container is the actual vessel that holds the liquid. In here is either insulation or a vacuum. Okay, they usually just suck all the air out of that and seal it. Okay, if they do that, then there's actually nothing in here. If there's nothing in here, can conduction occur between the outside and the inside? Okay, so that's a good way to insulate something then, all right, at least from conduction. All right. Now, what about convection? What states of matter does that occur in? Okay, not just gases, but also liquids. Any fluid, so liquid or gas. Okay, so occurs in fluids. If you're not writing this down, you really should be. All right, so it occurs in fluids, and this is okay, transfer of energy by circulation. Okay, hot air rises, cool air descends. This is the second law of thermodynamics applied. Heat flows from hot to cold. Okay, and most of the time that happens through convection, especially on Earth. Okay, since most of our heat is transferred through the atmosphere. Right? Convection in the atmosphere is called, four-letter word, starts with W. Wind. Okay, that's what you went over on Friday. Okay, wind. All right. It is the most important energy transfer mechanism. Okay, you talked about wind, you talked about the jet stream, okay, you talked about those little Hadley cells, okay, that move the air from the equator to the North Pole. If you aren't remembering any of that, you'd best watch that podcast again, all right, because that is super important for you to know. All right, so if convection is energy flow from hot to cold, let's go back to our insulated mug or thermos here. Okay, if I've got hot liquid now in here, the energy wants to go from in here to out here. Agreed? All right. The only way for it to do that is either through physical contact between the vessel and the outside, which we know there isn't any because we've filled this with a vacuum, or we haven't filled it, we've created a vacuum. Okay. If there's no air in here, no fluid of any kind, can I get that convection current set up in there? No, I can't. Okay? The only heat transfer method that will work through a vacuum is radiation. So creating a vacuum between the inside and the outside of a thermos is a highly effective way to insulate the interior, be it hot or cold. Okay, everyone follow me there? So the only way for that heat energy to get out is through radiation. Right? So what do we do with the inside of a thermos in order to make sure that we limit the amount of radiation that gets out? You make it shiny. Yeah. Okay. Either you make it shiny or you make it white. Right? One of the two, and both will work. Okay. In terms of reflecting the heat back in. Now, does your coffee eventually get cold? Yeah, because you know what? There still is some contact between the outside and the inside here at the attachment points at the top. All right? And usually there's also the opening. You have to drink out of it at some point. Okay? So when you open it, each and every time you open it, does air circulate through it? A little bit. And so you're losing some heat there. All right? It's not perfect, okay, but it does a pretty good job of insulating. All right? If you've ever had one of these and it gets ruptured, it immediately becomes useless. Okay, it no longer will insulate, okay, your coffee very well. All right, I have one that somehow got ruptured, okay, and water gets inside of it all the time. All right, and of course water easily convects energy right out through the skin, okay, and my coffee gets really cold if I use that one. All right, is there a way you could fix that? Theoretically, you could try and suck all the fluid, all the air and everything out of there and then seal it up again, okay? I mean, they'll work okay if there's air in there, but they don't work very good if there's water in there. All right? So what you do is, if there's water in there, there's also some air in there. If I pour really boiling hot water inside of here, what's it going to do to the air? It's going to make the air expand, and the air will actually push the water out the hole. That's how you can find where the leak is. Okay? And then you can find where to seal it off. All right? So there you go, something useful for you. All right? So you're going to need to apply these methods of heat transfer to some sort of practical situation. All right. Let's say I'm stranded in the Arctic. Okay. I need to get myself squared away and safe through the night. Okay. What should I do? I have basically no supplies. Okay, I'm in the Arctic. There's no trees, there's no caves. There's just dig into the snow. Why will that work? Okay, snow's white, so it's going to reflect some of my heat back at me. That's good. All right, what else? Okay, I'll be out of the wind because I'll build myself some sort of shelter. Okay, but I'm in the Arctic and it's wintertime, so the sun doesn't come out. But you're right, if I wore black in the daytime, that would work. In the nighttime, do I want to wear black? No, because black will absorb my heat and radiate it away quickly. I don't want that. Okay? If I'm wearing black, I'm in trouble. Okay, in the Arctic. In fact, how many people have ever seen the little survival blanket that comes in the survival kits? Anyone seen that? What's it look like? It's tinfoil. Okay? It's a tinfoil blanket. All you do is wrap it around you and it reflects your heat back at you. Snow is an insulator. Snow is an excellent insulator. Right? Here's why. Snow that is fresh, that is not compacted, okay, has air spaces trapped within it. Right? You've heard the expression, no two snowflakes look alike. Right? Well, the way snowflakes, when they fall, they interlock. They're jagged shapes, so they don't fit tightly together. They fit strangely together. And in between the snowflakes is air. That air can't move. So, if the air can't move, can this process occur? If the air can't move, I can't get a current set up, and I'm now safely insulated, okay, from my surroundings. My heat cannot convect out through the snow. All right. This is the same idea that we use when we use wool, okay, or like a Thinsulate or anything of the synthetic kind of varieties. Okay, all of that kind of stuff is essentially interspersed fibers. Okay, and when you have fibers, okay, like so, you get air spaces. All right, and those air spaces are trapped. Okay, the air that's in them is trapped. It can't move. It can't get out. It can't circulate, and as a result, it insulates against heat transfer by convection. All right? Since you also have air between you and the outside, conduction doesn't occur very well either, because conduction doesn't occur through a gas, only through a solid. All right? Everyone follow me on that one? Yes? Okay? So we generally want to build our insulators out of materials that are also poor conductors. Okay? Glass is a poor conductor of heat. Okay? What do we fill our walls with? What's it made out of? Fiberglass. Okay, that pink stuff that you see them putting inside the walls is fiberglass insulation. Okay? Glass fibers randomly kind of thrown together to create air spaces that cannot move. Styrofoam, same idea. If you've ever cut open styrofoam, there are almost microscopic little pockets of air inside. Okay? And that is why it is such a good insulator as well. It's also a poor conductor of heat. Okay, so these things all work very well. Okay? If I just have walls in my house that don't have any insulation in them, then they're full of what? Air. Hot on the inside, it heats this wall up, and then the second law of thermodynamics goes to work. Heat flows from hot to cold, and I get this circulation going inside my wall, and my heat moves outside very quickly. Okay? Where do you suppose your house loses the majority of its heat in the winter? Not through the walls. Not through the roof either. Your roof will have insulation. Doors and windows. Okay. Now, most windows are designed so that they have two panes of glass. All right, an inner pane and an outer pane, and either there's a dead airspace or a vacuum inside, or it's filled, okay, with like argon or something like that that does not transfer heat very well. Okay, that's how kind of your low E windows would work. All right, way back in the old days, okay, they used to always put on storm windows in the wintertime. Essentially, they slapped another window on the outside of all of their windows to create separation between the inside and the outside. Okay? And it acted as kind of an extra insulative barrier between in and out. All right, you guys following me here? So this is the kind of thing you're going to be asked to do in this unit, is apply all this heat transfer stuff, okay, that we talked about to some practical situation. When we have time in this unit, I actually have you build either an insulating device or a solar heating device, okay? One that can capture lots of sun and heat up water, or one that will reflect the sun and keep the water cool, one or the other. Okay, but we don't have time for it. We've run out of time. Okay, so I'm telling you about how you would apply this kind of stuff so you'll know how to do it on the exam. Okay, conduction, convection, radiation. That's how heat is transferred. Okay, and remember also the three fates, okay, of light when it strikes the earth. It's reflected, it's used or converted by photosynthesis, okay, or absorbed based on the albedo, okay, and then once it's in, then this is the stuff that can occur. Okay, once it's absorbed, what do we do with it? What happens to it? How does it get transferred from place to place? Caroline, question? It depends. Completely dependent on type of plants in the area, how dense they are, if they're tropical or grass or whatever. Yeah, it's completely dependent on that. Okay, and then again, remember guys that all of our weather, okay, are examples of convection. Okay, and convection, okay, that's wind. All right, so remember that we had that you talked about on Friday, the Coriolis effect. So if air is trying to move down from the pole, all right, but the Earth moves this way underneath it, it appears to come from this direction. Is that ringing a bell? Okay, if air is trying to move upwards, okay, it gets deflected this way. We're kind of in that band. That's why our prevailing winds come out of the west. Yes? Is that ringing a bell? Okay, got to know that. That's the Coriolis effect and how it causes the prevailing winds. Okay, that of course wouldn't occur if this isn't going on. Okay, there has to be air already moving, okay, for the rotation of the Earth to affect it. So prevailing winds are a combination of convection, okay, and the rotation of the Earth. All right. The other thing you talked about in the winds lesson was the jet stream. Okay, and the jet stream is that high altitude wind, okay, that can transfer stuff from the equator to more northerly regions. Okay, reason being, if this is the Earth, the jet stream's location changes all the time. Okay, it's always moving. When we get, a very sudden change in the weather, it's usually because we were, let's say, right here, and the jet stream moved past us and brought in a very different type of air mass. Okay, and then our weather can rapidly change. And we just happen to be in one of those areas where the jet stream yo-yos around us all the time. Absolutely, that's why it's called the jet stream. Okay, it's high enough up, okay, that jets will, when appropriate, attempt to get into it. Okay, because it can take significant amounts of time off of their flight. Conversely, if they're going the other way, they need to try and avoid it. Okay, otherwise it will slow them down. So planes file their flight plan based on where the jet stream is known to be while they're flying. Okay? And if that changes, they change their course and alter it. Okay? That's why sometimes, if you've ever flown, sometimes you arrive ahead of schedule. Okay? They're like, oh yeah, well we caught the jet stream and we're arriving 6 or 7 minutes early. Okay? It doesn't make a huge difference, but it makes a bit of difference, and it actually makes a difference in terms of the fuel they use. So pilots are, of course, always encouraged to try and get into the jet stream because it allows them to use less fuel. All right. Okay, so jet stream, that's important because obviously as it fluctuates like this, it can bring air masses from southerly regions to northerly regions and vice versa. Grace, yes. Okay, everybody with me there? All right, okay. Other things here to kind of go over. Okay, when we were talking about the factors that affect climate. Okay, the factors that affect climate. Okay, we said latitude was the biggest one. Okay, reason for that, obviously, as you get further away from the equator, the intensity of the sun decreases. Okay, we also said that altitude played a factor. Okay, those are kind of the big ones, and we reinforced those when we did the climatograms activity, which you handed in today. Okay, proximity to mountains, proximity to oceans, regions of high and low pressure. Okay, all of these are important. Okay, because it's the interaction. It's not just one. Okay, it's usually the interaction of several factors that influences the climate of an area. Okay, and these high and low pressure areas, they greatly influence our wind. Okay, you probably noticed that generally the wind comes from the west here, but if we're about to get a major change in weather, it comes from some other direction. Right, especially in the winter time. Right, if we're about to get a nasty, nasty storm, which way does the wind come from? Nope. If it comes from the mountains, we're getting a Chinook, and everything's going to be just fine. Northeast. Nothing good, meteorologically speaking, comes from that direction. Okay, it always brings in Siberian high-pressure air. All right, so that means cold and dry. Now, that's okay. It's going to be cold and dry. The problem is, if we're here, okay, and we've got a high pressure, cold air mass moving towards us, and out here on the coast, we've got a low pressure area that's got lots of moisture moving in this way. Okay, when those two things interact and they hit right here, they go this way. Okay. You ever noticed how whenever we get a snowstorm, it seems to follow exactly down Highway 2? Okay, yeah, well, that's because that's where those two things, high pressure area, low pressure area, that's typically where they are, okay, up in the north and over here, and when they come together, okay, they create this huge interaction that always seems to happen right on top of us. Okay, now, there's also rotation here. Okay, you got cold, you got hot. Okay, heat always flows from hot to cold, and so while we're transferring that energy, usually after the storm, okay, the weather kind of changes as the energy balances out. Caroline. Because they get a lot less of this stuff than we do. Okay, there seems to be a spot in the mountains that these kind of air masses like to come through. It's right around Old Stidsbury. That spot seems to be the spot where it likes to come through the most. So typically, Edmonton gets more of the high-pressure Siberian stuff, and we tend to get more of the right off the mountains, okay, lower-pressure stuff. Okay. Yeah. All right. Is this ringing a bell for everybody? All right. So it's really important that we understand, okay, all of that kind of stuff. Okay. What was the other thing I wanted to talk about? Couldn't have been that important then. Okay, I'm going to go over how many people have done the specific heat capacity worksheet that I gave you the other day. How many people have done the whole thing? Okay, how many people are close? All right, that's kind of what I thought. All right, we're going to move on to latent heat then. Okay, so take out your notes. You need the latent heat stuff. Okay, it should be lesson 6, I think. Yes. All right, now, we talked briefly about latent heat when we were in lesson 2, okay? And we said that it's also one of the ways that energy gets transferred from the equator to more northerly places, because it takes energy to evaporate water. Okay? Once that water evaporates and it moves somewhere else, when it condenses, all of that energy gets released. Okay? So it's an important energy transfer mechanism. Okay? And the jet stream is part of that. It pulls these kind of moist air masses from the more equatorial regions, brings them up, okay, to our area where they not only release the moisture, but also this latent heat. And once that moisture condenses, it becomes sensible heat. Okay, that means our energy goes up, our temperature goes up. All right, everybody follow me there. What we want to look at now is mathematically, how much energy is that? Okay, and it's huge. Okay, the amount of energy that that represents for us is huge. All right, so what we're looking at in this diagram here is what we call the heating curve of water. Okay, what it shows is how much heat gets added and then what happens to the temperature of the water as a result. Okay, so we start out on this heating curve down here at minus 25 degrees Celsius. What state is water in at minus 25 degrees Celsius? Solid. Okay, you can supercool liquid water down below that. Okay, but you have to be very careful. As soon as you get any type of crystallization occurring, it will flash freeze. Okay, and all of it will become solid like that. Okay, I actually had a chem prof in university who brought in this container. It was insulated with liquid nitrogen, and what was inside of it was supercooled liquid water. This liquid water was like minus 30, right? But it was a liquid, right? And he showed it to us, and he had it kind of in this beaker that he very, very gently sat down on the counter, okay? And all he did was sprinkle a tiny little bit of salt. And as soon as that salt hit the water, it flash froze and shattered the beaker. Okay, because it expanded rapidly, because obviously ice takes up more space than water does. Okay, expanded rapidly, broke the beaker. Okay, and there was this block of ice sitting there, and it had frozen in like the snap of a finger. Right, it was very, very cool. Now you can see this happen if you've ever done this. You put some bottles of water in the freezer, right, and then you pull them out, and you know they're still liquid, but as you take the lid off and go to turn it upside down, it freezes on you. Okay, very slowly. Right? It's the same idea. You've cooled the water below its freezing point, but the crystallization process didn't happen right away. But as soon as you turned it over and the bubble traveled through, that starts the crystallization process. Okay, you can do the same thing if you just take it and bang it on the. I think I have a video of it. I'll show you it later. Okay, bang it on the counter, it'll freeze. Okay, freeze very rapidly. Right. Again, this has to do with latent heats. You've taken all of that energy away, okay, and then when it finally changes state, even more energy gets released. All right, so we're down here, minus 25 degrees. As I add heat, obviously, what happens to the temperature? The temperature of the ice should go up. Okay, does the ice start to melt right away? Ice doesn't melt till it gets to what temperature? 0. All right, I can add heat to ice and the ice won't melt. All right, if I add it slowly, the ice will just get warmer. Typically, we don't see that because if you put ice in your hand, the outside of the ice cube starts to melt right away. Okay, because you rapidly heat up, okay, the outside of the ice cube before the inside. Okay, but in the perfect physical world, okay, ice doesn't melt until I get to 0 degrees Celsius. So I get the temperature going up here. Okay, then I get to 0, and then the temperature stops changing. I continue to add heat, but the temperature doesn't change. Well, what's going on with the ice? It's melting. Okay? The temperature of the ice will not change until all of it is melted. All right? So the ice-water mixture will stay at 0 degrees Celsius till all the ice is gone. All right? We use this all the time. That's why we put ice in drinks. Okay, the ice will absorb energy and the temperature of the liquid will fall back down to around freezing until all the ice is gone. And then your drink starts to get warmer. Everybody with me? Okay, so that's why we do that. Okay, it takes a lot of energy to change the state of something. Right? Way more than it does to just increase its temperature. Right? That's latent heat, the amount of energy required to change the state of something from one thing to another, liquid to gas or solid to liquid. Okay? All right, so during this time here, I'm adding energy, but the temperature is not changing. So, temperature measures kinetic energy of an object. State measures the potential energy of an object. I can't change both at the same time. When we're talking about thermal energy, I can only change kinetic thermal energy or potential thermal energy. I cannot change both at the same time. All right, so I'm adding heat, I'm adding heat. Eventually, all of my ice is gone. Now I'm here, I've got water at 0 degrees Celsius. I continue to add heat, what happens to the water? It gets hotter, right? The temperature goes up, okay? And that's what we see here. Temperature goes up, then it gets to boiling. Once it starts to boil, what happens to the temperature? It stops changing. Liquid water won't exist above 100 degrees Celsius under normal conditions. If I put it under pressure, I can heat it more than that. Okay? But under normal conditions, the water will just boil and boil and boil and boil and stay right at 100 until all of it's gone. Right? Once all of the water is gone, then the steam will start heating up. Okay? Now, look how much energy I have to add in order to turn this water from liquid to gas. Is it a lot more than I had to add to turn the same amount of ice into water? Yeah. All right. Now, think back to what we were talking about a few minutes ago. A moist air mass moves in from some place in the tropics to here, and all of that liquid water condenses and falls as rain. Is that a lot of energy being dumped here as well? Yes. Okay. A lot. All right. So, there's two types of latent heat. There's the specific latent heat of fusion. That has to do with melting ice or freezing water. Okay? So the change of state between solid and liquid. All right? Now, certainly it takes a fair amount of energy to do that. You've all made a snowball with your bare hands at some point. Okay? You know how cold and how quickly your hand gets cold when you do that. All right? Because you're rapidly giving energy away to the snow. And what's the snow doing? Well, first it's increasing to 0. That doesn't take very much energy. It's the actual melting of the ice, okay, melting of the snow that absorbs that much energy. All right? Everybody with me there? Yes? Okay. Can an ice cube keep a drink cold for a long time if that drink is, let's say, around 5 degrees Celsius when you throw it in? Sure it can. Okay? What if the drink is at 25 degrees when you throw in the ice cube? It's going to melt pretty quick, but is the temperature of the drink going to go down considerably? Yes, because that ice cube is going to absorb a lot of the heat from the drink in order to melt. Okay? Everyone follow me there? It takes a lot of energy to melt ice, and so even one ice cube in a reasonable sized drink, okay, can reduce the temperature of that drink considerably. All right. The other one is the specific latent heat of vaporization, and this has to do with either condensing a gas back into a liquid, okay, or evaporating a liquid into a vapor. Now, which burns you worse? Steam at 100 degrees Celsius or water at 100 degrees Celsius? Steam. Why? Not so much that it's everywhere, so is the water. I mean, if I stuck my hand in water, it'd be completely... Not that I would do that, okay, right? But it'd be completely surrounded by water in the same way that if I stuck it into steam, it would be completely surrounded by steam. There's more energy in steam. Look here, okay? Here's water at 100 degrees Celsius, okay? It's only got 15 kilojoules of energy, okay? Here's the same amount of steam at 100 degrees Celsius. It's got 55 kilojoules of energy. Is that a lot more? A lot more. All right. It takes a lot of energy to separate those water molecules from their liquid state to their gaseous state. All right. And when they go back together, they release all of that energy. All right. So if you were to be scalded by 100 degrees Celsius water, certainly that would be painful. Okay. But you would only receive a mild burn. If you were to be scalded by steam that was at 100 degrees Celsius, you would receive deep tissue severe burns, because not only is that steam 100 degrees Celsius, it's got all this extra potential thermal energy, and when that steam hits you, it's going to condense back into a liquid form. All right? And when it does, it's going to release all of its latent heat onto your skin, and as a result burn you way worse than the same amount of liquid water could ever have. All right, so that's why you're always told to stay away from the steam, right? Okay, the steam can really, really burn you badly because it has so much more thermal energy, okay, than liquid water does. Okay, now let's think of it another way here. How do we keep cool? What does our body do to keep cool? You sweat. Why does sweat keep you cool? Okay, when you sweat, what temperature is the sweat? Same as your body. Okay, everyone goes, well, it's water, so it keeps you cool. It's 37 degrees Celsius water. It's like tepid. It's disgusting. Okay, if that water gets out on your skin, it isn't any cooler than you are. But once it gets on your skin, you do feel cooler. Because where's it going? To the outside. When it gets onto your skin, it starts to what? It starts to evaporate. Where does it get the energy from to do that? From you. Okay? You give the energy to that liquid water in order to make it evaporate. If you're giving energy away, you should feel cooler. Okay? It takes energy to evaporate sweat, right? And that's why we feel cooler. It's the same reason why when you get out of the shower, you feel chilled, right? You get out of the shower and you're wet, okay? You step up into the and as a result, you get cold. Right? This is also why we're always told in the winter you should dress in layers. You should always dress in layers. All right. Reason being, if you're standing around, you want to have all your layers on. But if you start working, okay, you don't want to get overheated because what will you do? You'll sweat. Okay. If your clothes get wet and then you stop working, what's going to happen to the water? It's going to evaporate. Where's it going to get the energy from to do that? You, and you're going to get chilled. All right? That's what you'll often see, okay, like athletes and climbers and you know, hikers and whatever, they're taking layers off before they get too hot because if those layers get wet, they're useless. Okay? When they put them back on, water will still be there. Okay? And when it starts to evaporate, it's going to use your body's heat to do it. Okay? That's also the design behind new that get the moisture away from your body. Okay? You guys, anyone kind of worn those? Okay? When it pulls the moisture away from your body outside, now the shirt separates the moisture from you, and so when it evaporates, it's not taking the energy. And you stay. All right, and you also in hot conditions feel so gross. All right, because it's working